So, are there any questions? All right. So we were talking about Grassman variables last time, and I think that I find them kind of spooky. Maybe you find them spooky. I think that at one point, I don't know when it was, people found I to be spooky. In other words, that I squared is -1. And well, we've grown more relaxed about that, certainly. So presumably we'll become more relaxed about Grassman variables at some point. So let me just remind you what the deal is. Basically, let me say, well, the theta squared is 0. So the most general function is a plus b theta. And the most general integral, in fact, I'm wondering when will Mathematica do integrals of Grassman variables? Do they do them yet? Does anybody know? That's, I suppose once Mathematica does them, people will relax. All right, anyway, the most general thing is then an integral of a d theta plus let us say b integral of theta d theta. And what we want is to define these two integrals. So the total integral table is what's the integral of d theta, what's the integral of theta d theta. And the idea is you want this thing to be the same as the integral as this thing, because this is just a shift. And the idea is we're integrating over all theta. And so what is this? Well, this is certainly there's the function. So it's a plus b times theta plus zeta d theta. And so this thing is, well, a plus b zeta d theta plus b integral theta d theta, rewriting it this way. And so we see if we want these two things to be equal, then we can have the integral of theta d theta equal to anything, because those two terms will be the same. But here this term has changed, and so we better set the integral of d theta to be 0. So that's our integral table, that this thing is just b. In fact, we're going to say the integral of theta d theta is 1. So the integral of f of theta is just b, and over here this is again b.
Is zeta another Grassmannian?
Excuse me.
Is zeta some arbitrary Grassman?
Yeah.
Then why can't we? It seems like we're being more specific than we could be in saying that that first integral is 0. You could just say that the integral of some Grassmannian over a different one is equal to 0.
Okay, I'm sorry. You're saying now
so
what?
We have integral of a plus b zeta d theta.
Here.
Yeah.
Okay.
So you just said
we
that
want that this should be a integral d theta. And in other words, this rewriting this is a plus b zeta.
Yeah.
So we want this to equal that.
Which means integral of b zeta d theta is 0.
So you're saying all we need is to say that integral
Yeah, so it seems
of
like we're being less
zeta d theta is 0.
Yeah, so is that,
Yeah, okay, so that's, no, you're right.
But zeta is arbitrary.
yeah, that's just two, those are two completely unrelated.
I think that what you're saying is correct. I think, though, that what happens is that this has to be true for an arbitrary
Right.
Grassman variable.
Right.
And all right, so let's say the following. Suppose integral d theta is a complex number, not 0.
Yeah.
Then this thing is equal to zeta times z, where z is not 0. Well, then we would find that zeta had to be 0. So we started out with zeta arbitrary Grassman, then we find it's not only not Grassman, but it's 0.
All right.
So, of course, the other possibility is we can say, well, by fiat, we're going to say that we adopt this rule because it gives us the shift property, and that we're forced to it. Well, we're not quite forced to it, perhaps. Good point. Oh, here, you get at least one. Do you want another, or are you worried about your
I'll
teeth?
take another one.
Take another one. All right. Okay, so that's our rule. Integral d theta 0. Integral theta d theta equal to 1. Okay, and of course we could have chosen this to be 13.5 or something, but that would have made all subsequent calculations unnecessarily clumsy. Now, we would normally stop here, and we might stop here if our fermions in the real world were real as opposed to complex. But since all the fermion fields are complex, as far as we know, we think of having a fermion field psi and a fermion field psi delta, or if you want psi star. So if we're thinking that the fermion operators are complex, then it's natural to say, well, let us have theta and theta star, let's have these independent variables. So because our fermion fields are complex, we're going to use, we're going to start out with complex, effectively complex Grassman variables. And I'm thinking here now of a single mode of a fermion field, a complex fermion field. And so what we've got then is that the anti-commutator of psi with psi dagger is, of course, psi dagger plus psi dagger psi. And that this is going to be 1. And on the other hand, that psi squared equals psi dagger squared is, of course, going to be 0. And this, of course, is this business of that these things are fermions, and that's related to spin and statistics, and the wave function has to be totally anti-symmetric. And we know all that, and also we know that that has enormous physical consequences. Atoms would everything would be in the S, well, I don't know what state it would be in, but the atomic structure, nucleic structure, everything almost depends upon this. And yet, truth be told, although we understand the mathematics, we don't understand why fermions anti-commute in the physical sense. That is to say, how is it that, or equivalently, how is it that under rotations fermion fields transform as an SU2 doublet? Okay, so there's something there that we don't understand. It may be that string theory has or will explain this. I don't remember, and so that's something I always meant to look into and never quite have. So we should just keep in mind that although we know this is the right mathematics, we don't understand what's really going on. So what we're going to have then, instead of one theta, we're going to have two thetas. And there we're going to have theta star squared equals to theta squared equals to 0, of course. And we're also going to have theta star theta plus theta star be 0. In other words, everything's going to anti-commute to 0 because it's these things are numbers, whereas these guys are operators, so their anti-commutator is 1. We can go through the same logic here with theta star rather than theta, and then we come to the conclusion the integral d theta star is 0, integral theta star d theta star is 1. Okay. So now we've got complex Grassmann variables. We know what the integral table is, and so the next step is to talk about some state. And we're going to have a state 0, and we want this to be a state that's annihilated by psi. And so what do we say? Well, what we say is that this, we're going to define this as psi times some state S with the condition that that's not equal to 0. So notice what we mean here. We pick some fiducial or reference state S, and the only thing we insist upon is that it not be annihilated by psi. Otherwise, our states, our vacuum state is going to be 0. We don't want that. So we say, we assume that there's some state psi that's not annihilated by this, and that certainly makes sense because, after all, the anti-commutator is 1, and if there were, actually, now that I think about it, I'm a little puzzled here, because if I take the mean value of this thing in the state 0, I'm going to get 0 on the left-hand side and 1 on the right-hand side. All right, let me continue with the story rather than go off on these tangents. Anyway, this is the reference state. This is going to be our state 0. And what do we have? Well, we have that psi on 0, of course, is psi squared on the reference state, so that's equal to 0. And as I said, this bothers me a little bit because if we take the mean value of that top equation in this state, we're going to get 0 equals 1, which is a very bad equation. So in other words, if we took 0, this is going to be 0. On the other hand, it's 0, 0 with a 1 here, and that presumably is 1. So that's something that I'm missing there. Oh, no, no. All right, I don't know. Something fishy, something that I never noticed before that is an issue here. Let us just call this an issue or a problem, but I think I should go around it because what I'm following here is the standard way of discussing these things. And
where are you getting the 0?
That's what I'm wondering.
What?
Yeah.
Why are you getting that the left-hand side is 0?
excuse me?
Why are you getting that the left-hand side is 0?
Well, because psi annihilates 0. That was this equation.
Sure, so that's that term.
And if you take the oh, great, bravo. All right. I was just being stupid. Okay, good. Physics is saved. The point is that psi, this thing implies 0 psi dagger is 0, not psi. So we're not, we don't have a problem here. Okay, so both of you guys get another, sorry. Oh, damn it. All right. In fact, you're entitled to a second if you want. You want another one? Anybody want another one? All right. Is somebody else hungry?
Sure, I'll take one.
Yes.
Please.
All right. Better to ask a question. Okay, so physicists say that we can move on. So this, so inasmuch as psi squared is 0, psi on 0 is in fact 0. And now we're going to define something. And this is a fermionic coherent state. Now it's a bit of a pity that I haven't talked about ordinary coherent states, and we're doing fermionic ones before bosonic ones. But in any event, this is e to the psi dagger theta minus a half theta star theta on this ground state. And while I'm at it, I might as well define the coherent state for a single harmonic oscillator. This would be e to the a dagger alpha minus a half alpha squared on the ground state. Okay. So that's the coherent state alpha. It turns out that that's an eigenstate of the annihilation operator with eigenvalue alpha, alpha here being complex. And now we're going to see the same thing is true for theta, namely that it's an eigenstate of psi with eigenvalue theta. First of all, what is this state? Well, if we expand these terms, we get 1 plus theta psi dagger theta minus a half theta star theta. There's a cross term, but it's 0 because theta squared is 0. So it's all of this on the ground state. All right. Now, suppose we have here psi on theta. Well, this is psi on 1 plus psi dagger theta minus a half theta star theta. And what's that? Well, the psi on 1 hitting that, that's going to be 0. The psi on this term is going to be 0. So this is just psi dagger theta 0. And on the other hand, this thing is 1 minus psi dagger psi theta 0. Psi dagger anti-commutes with theta, annihilates 0, and so this is just theta 0. By the way, I mentioned all these anti-commutation relations. What I forgot to say is that theta and psi anti-commute. So in other words, the Grassman variables not only anti-commute with each other, but anti-commute with all fermionic operators. Okay, so that's that. What is theta theta? Well, theta theta is theta times 1 plus psi dagger theta minus a half theta star theta 0. Okay. Well, that is certainly theta 0, but all the other terms vanish because theta squared is 0 and theta hitting that is 0. So that's that. So what do we find here? It's sort of almost unintuitive. It's that psi dagger on theta gives us something that's the same as theta on theta. So in other words, since theta on theta is psi on theta, we have the rule that psi on theta is theta on theta. Okay. So this state is an eigenstate of psi with eigenvalue theta. Now, you might say, is this eigenstate of the fermionic field or fermionic annihilation operator, is it unique? Well, no. You could get rid of this normalization factor. In other words, you could define some theta prime equal to just e to the psi dagger theta on 0. This also would be an eigenstate. It just has different norm, different Grassman norm. The same thing is true of the eigenstate of the bosonic annihilation operator. We could define one that was e to the alpha a dagger on 0. That just is not normalized to unity. And so some people, in fact, prefer this normalization. Okay. Now, if we take the adjoint of this state, and in fact, the adjoint of an arbitrary fermionic or Grassmannian coherent state, what we get is 0. Well, what is it? It would be the adjoint of this with theta replaced by zeta, and that's 1 plus zeta star psi minus a half zeta star zeta. So that's the adjoint of the coherent state with eigenvalue zeta. And now we can compute the inner product of the two. And I think maybe I will compute this in detail. This is one of the things that I made a homework problem, but I think it's probably useful to go through it. This would be 1 plus zeta star psi minus a half zeta star zeta, and then this part is over here, and it's 1 plus psi dagger theta minus a half theta star theta on 0, or ground state of the vacuum, or whatever. Okay, so let's see if we can simplify this. Of course we can, but certainly the one state hits all that, and what does it give us? Well, basically everything survives, but not psi dagger on 0. Right? That's your theorem. So what we get then is 1 minus a half theta star theta from multiplying by 1. Now we multiply by this term. And what we get is psi dagger, well, the psi dagger psi term is going to go away because psi annihilates the vacuum. So we can forget about that term. The next one is this one times that one. And so I'll just write that down. Zeta star psi dagger theta. Okay, that one survives. But this last one doesn't because psi annihilates the vacuum. Right. All right, now we've got this one. This one times this, that survives, minus a half zeta star zeta. This one doesn't because psi dagger annihilates over there. And then we get this term, which is 1/4 zeta star zeta, theta star theta, and all this is inside the vacuum. Okay, well we can rewrite this as 1 minus psi dagger psi, and then this annihilates everything. Okay, so what we're left with is 0, 1 minus a half theta star theta, plus zeta star theta, minus a half zeta star zeta. Wow, that's some zeta. I remember I once wrote a paper and some guy with a zeta in it, and one guy said to me, "What's lightning?" Plus a quarter zeta star zeta, theta star theta. All right, so that's what we've got. And now it turns out we can rewrite that in a somewhat simpler way. We can say that this is what? 0 e to the zeta star theta minus a half zeta star zeta plus theta star theta. And so, I mean, expanding this, the first term gives us the 1. The linear term gives us that. And then the linear term in this gives us these two terms. The square of this term gives us that term. Notice that zeta star zeta commutes with theta star theta. And you might wonder, how did you get a quarter? Well, when you bring this thing down, the second power of this gets an extra 1/2 from the expansion of the exponential. So you've got an 8, then you get a doubling to a quarter. Okay, on the other hand, this is entirely Grassmannian, and so it doesn't affect this, and so we just have 0, 0 is 1. And so this is e to the zeta star theta minus a half zeta star zeta plus theta star theta. Okay, so that's the inner product of two fermionic coherent states, and it may remind people. Let me just write down what the inner product of two ordinary coherent states would be. it's e to the beta star alpha minus a half alpha squared minus a half beta squared. So that's the inner product of two ordinary coherent states. And the absolute value of this squared, of course, then is you get this plus its complex conjugate, and then you get these guys with a minus 1. And so that turns out to be e to the minus beta squared. And so you see when alpha is equal to beta, the thing's normalized. Okay, so this thing looks very much like the bosonic analog. And one reason why it does is that whenever you have anything that's quadratic in fermionic variables, then you've got something that's that behaves like a complex number, because the product of two Grassmann variables, if they're not the same Grassmann variable, then commutes with product. In other words, any two quadratic forms in Grassmann variables commute. So they behave like complex numbers. Okay, now there's a formula that's worth looking at, namely integral e to the c. C is a complex number. Theta star theta d theta star theta. Well, this is an integral of 1 plus c theta star theta d theta star d theta. Well, first of all, we rewrite this as 1 minus theta star times c d theta star d theta. And of course, the part that you might think is non-zero, this is the zero term, because d theta star is 0, d theta is 0. And then what we have is theta star d theta. Well, that's 1. So this gives us minus c theta d theta, but that's also 1, so the answer is minus c. All right. Okay. All right, now let's consider what's an arbitrary state in this fermionic space. And it's C0 plus D1. And by that, what I mean is C0 plus D psi dagger 0. So here's psi dagger takes us from the ground state to the first excited state of this simplest complex fermionic system. The thing that is causing my head at the moment is a kind of another issue. I should banish all these issues while I'm lecturing, I think, but it's normally if we have a complex fermionic field, then we really have two excited states. We have the particle and the antiparticle. And so where's the antiparticle here? And I don't know. And I guess the answer is that this is not playing the role of a field, this is playing the role of a fermionic creation operator, which makes sense. Okay. And what we would have to have was another fermionic creation operator, which is complex, which would create the other state. Okay, anyway, this is what we've got. And now what's the identity operator in this space? Well, it's clearly this plus 1, 1. That would be our identity operator for this space. Turns out that this is equal to this expression here. And now I normally would just assign this as a homework problem, but I think because these Grassman variables are so spooky, I think it's good for me to do some of these, do more of these things in class. So what would this be? Well, what is theta? Well, the theta state is either the psi dagger theta minus a half theta star theta. So, or maybe expanded is better. So let me expand it. So this is 1 plus psi dagger theta minus a half theta star theta. And we're assuming, we're treating these things as bosonic, by the way. And so this is 1 plus theta star psi minus a half theta star theta. And then, of course, we have d theta star, d theta. The choice of whether it's d theta star, d theta, or d theta star, that's sort of arbitrary. You set the thing on one way or the other, and you get one set of answers or the other. And in the end, it doesn't really matter. Okay, so what is this going to be? Well, first of all, let's again start with the 1. 1 times this times 1 integrated 0. So in order to get something non-zero, we need both a theta and a theta star. Okay. And so one way of getting a theta and a theta star is having this thing times that times 1. And in fact, when the theta star theta hits the differentials, the thing is backwards. And so we need to bring the theta star forward. That changes this to a plus a half. Same thing with this one, this one, we flip them. In fact, why don't I just flip them right now? Plus now we see that this thing and that thing give us the state 0, 0. So this is part of the answer. What's the rest of the answer? The only other way of getting theta star theta is to use both side states. And that would mean then we have an integral psi dagger 0. And then I'm pulling the theta through. I'm going to pull it through these two guys. And so well, I'm going to, all right, maybe I should do this in 2 steps. Okay, that's the only other way of getting a theta star and a theta. Okay, pulling this through, we get a minus sign and a 1. Then pulling this through the psi, we get another minus sign and a 1. And so this gives us 0, 0 plus psi dagger 0, 0 psi. But psi dagger 0 is what we mean by 1, and so this is just 0, 0 plus 1, 1. And this is what we call the identity operator for this smaller space. Okay. So, I hope that some of the mystery has disappeared here. At the very least, it's covered with fatigue, if not clarity. Okay, well, the next thing, of course, is to realize that. By the way, one thing that I forgot to mention here is d theta star, these things, anti-commute, d theta with any psi, anti-commutes, the anti-commutator of d theta with any theta or theta prime, that sort of stuff. So all of these Grassmann variables anti-commute with everything. Okay. All right. The next thing, of course, is that we want to introduce several fermionic variables, several Grassmann variables. And so what we'll have is theta 1, theta 2, theta n, and of course also theta 1 star, theta 2 star, theta n star, and we'll have psi 1, psi 2, psi n, psi 1 dagger, psi 2 dagger, psi n dagger. Okay, so we have this space. The Grassmanns anti-commute with all the fermionic variables, and we can think of these as annihilation creation operators if we want. What else? Oh, but since these are actually the fermionic operators, we have psi I, psi j dagger, anti-commutator is delta ij. So that's the relation we expect for the fermionic operators. And of course also any two psi's anti-commute, any two psi daggers anti-commute. Okay. What's the ground state or the vacuum state? Well, it's 0 and it's going to be a product. K equals 1 to n of psi k on some fiducial state S, and the thing we're going to insist upon about S is that after it's gotten hit with all these psi's, that it's not 0. And so we pick such a state. And because then the other thing that I guess forgot to mention is we want to say that this 0, when hit by all of those guys, that it has unit norm. And in fact, we also want to say that it's bosonic, don't we? Because that's something that we used over here, for example. We said, well, of course we have two of them here. So in a sense it doesn't matter. Maybe we don't need to make it bosonic. Okay, anyway, let's take that our fiducial state, and then we're going to do the same thing, namely we're going to define a coherent state, but now this is more elaborate because now this is a sum. K equals 1 to n, and it's going to be psi k dagger theta k minus a half theta k star theta k. That in an exponential acting on this ground state. All right. And of course we can multiply this out. We can say, well, this is just a product, k equals 1 to n, of 1 plus psi k dagger theta k minus a half theta k star theta k on that. Now, notice this thing has been explicitly constructed in terms of things that are themselves bosonic because they're quadratic and fermionic variables. Since they're bosonic, the order in which we multiply these factors doesn't matter because they commute. Now, what is psi k on theta? Well, what we can do is we can say that the psi k is obviously going to commute with all these bosonic things as long as, well, let me call this L. This will be then the product k not equal to L of 1 plus psi k dagger theta k minus a half theta k star theta k, and then it'll be psi L on 1 plus psi L dagger theta L minus the half theta L star theta L. So that's what this is. But this is just the coherent state formula for the variable psi L with argument theta L. And so we know that this just gives us ditto theta L ditto. Now we can pull this guy through all these bosonic variables, and what we get is theta L theta. So this fermionic coherent state is also a coherent state for all of these fermionic variables. And this is also very much similar to the case where if alpha is an interval of complex numbers, the analogous thing is some ak dagger alpha k minus a half alpha k as value squared on the ground state. So that's the bosonic analog. There's a perfect parallelism here, and many years ago, before you were born, most of you at least, Flower and I wrote some papers on coherent states, and then about 20 years ago, when he was visiting here, we wrote a paper on fermionic coherent states, and the parallelism was amazing. These are all phys rev papers. Okay, now there's one more thing that, well, infinite number of things to look at, but the next thing to look at is basically why we need these Grassman variables. Well, suppose we have psi L psi k on some state theta, and suppose this state theta is an eigenstate of both of these fermionic operators. Now, the way we have constructed it, this is then psi L. This would be theta k, theta. And now, because theta k anti-commutes, this is minus theta k psi L, theta. And then this is minus theta k theta L, theta. And because this is the same thing as theta L, theta k theta. So if you have two fermionic operators ordered one way, the Grassman eigenvalues come out that way. Okay, and everything's fine there, because of course this is the same thing as minus psi k psi L on this state theta, and on the other hand, this thing, it would be, if we interchange them, we get minus theta k theta L on theta. Notice that we get in trouble if we try to have states with complex eigenvalues of these Grassman variables, because then what we would get, we would have psi L psi k on some state z, and this would give us psi L zkz, and this would then, if this is complex, this would give us zk psi L z, and this would give us zk zl z. On the other hand, this thing's Grassmannian, I mean, these things anti-commute, so this would be psi k minus psi k psi lz, and that would give us minus psi k zlz, and that would be then minus z k zlz. So we get a perfect contradiction here if we try to have states that are eigenstates of the fermionic operators with complex numbers as opposed to Grassmann numbers. So all this mathematics works out very well, but of course what's missing is what the hell is going on physically. All right. Now, we derived in detail, maybe I should go over here. We derived in detail what the inner product of two fermionic coherent states were. We saw it was this. And so if we go over here and define this coherent state in terms of many Grassmann variables and many fermionic operators, then since all of these things are bosonic and anti-commute with each other, we just get the same thing repeated over and over again. And so what we have then is that zeta theta is equal to 0 product k equals 1 to n, 1 plus zeta k star psi k minus a half zeta k star zeta k times the product L equals 1 to n, 1 plus sine L dagger theta L minus a half theta L star theta L 0. And of course, going through the same logic as before, this is equal to e to the sum k equals 1 to n of zeta k star theta k minus a half zeta k star zeta k minus a half theta k star theta k. So it's that exponential. It's just a repetition of that formula for each of the theta variables. Another way of thinking of it is to use vector notation. Then this thing is e to the zeta dagger theta minus a half zeta dagger zeta plus theta dagger theta. Okay. Dot products. All right, well, we derived the identity operator over here. We found the identity operator was a double integral over coherent states. In fact, let me write down the bosonic equivalent. The bosonic equivalent is 1, which of course is sum n equals 0 to infinity, n. These are all the n states of the harmonic oscillator. This, in fact, is equal to alpha d2 alpha over pi, integrated over the complex alpha plane. So the corresponding identity operator for several fermionic variables is the outer product of these multi-fermionic coherent states times a product k equals 1 to n d theta star k d theta k. And so that's that. Of course, one can have a different definition of these things, but then you have to check the arithmetic that it actually works out. All the authors perversely use different conventions. I suppose that's what leads to the religious wars of the Mideast. Kissinger once made a remark of this. I wasn't there, so I don't know. But he's reported to have said that the reason why arguments among faculty are so vicious is that there's so little to fight about. I'm pretty much right, actually. Okay, so that's our identity operator. Now, let's come to something that's, that I treated as an example in the book, but which is really, really very important. And so I think we should do it in some detail. G of A. A is a matrix. And here I'm going to do the simple, the first non-trivial case, namely 2 by 2. So this is an integral, this is a Gaussian integral, e to the minus theta dagger A theta. So theta is a 2-component vector, and so we can have that. And then we are going to have d theta 1 star, d theta 1, d theta 2 star, d theta 2. Notice if you choose to write in this way, the order doesn't matter because this is bosonic, so it commutes with the other. Whereas if instead you put all the theta stars together and all the thetas together, then you're asking for trouble. Okay, so let's expand this exponential. Well, obviously, because we have these marvelous integral tables, which mean that everything's 0 or 1, the only term that survives is a term that has theta 1 star, theta 2 star. So we can expand this and see what we get. So in particular, if we expand this, the first term is 1, that integrates to 0. The next term will be quadratic in theta, that integrates in 0. You need something quartic. So it'll be the quadratic term that will count. The cubic term, well, that's going to be just 0. And so we can forget about that. So what we've actually got here then is integral 1/2 theta star k AKL theta L squared. And then let me say this, well, product d theta star d theta. Product 1, 2, of course. Okay, so what do we have here? Well, this is going to be the following: 1/2, and now let's just write this out. Well, it's going to be theta 1 star A11 theta 1 plus theta 1 star A12 theta 2 plus theta 2 star A21 theta 1. Notice the left arm is down, so you need to watch it. Theta 2 star A22. I went off the rails right away. And now our product d theta star d theta. All right, so what are we, squared. Okay, so, well, the square of this term, forget about it, because we're not going to have, we need one of each, and only one and only one of each of these variables. So this squared, that squared, 0. So it's only the cross terms, but they have to be the right cross terms. This with this 0 because theta 1 star squared is 0. But we have this with this will be non-zero. And notice these things are quadratic and fermionic variables, so they're effectively bosonic. And so this then, we can say we get this times that plus that times this, but we can just cancel the 2 and write it as theta 1 star A11 theta 1 theta 2 star A21. Oh, oh, I got it. This is 0 because it's theta 1 squared. So it's just this times, no, that's 0 also. I'm having trouble. Oh. That one's 0. It's just this one. These two will work. Okay. So the first times the last. The next is these two guys obviously work. And so this is plus theta 1 star A12 theta 2 theta 2 star A21 theta 1, and all of that product d theta star d theta, by which I mean this. And the thetas can be in arbitrary order, but these guys, you don't want to screw around with them. Okay. So what do we have? Let's look at this one. The theta 2 star, well, maybe I should write it more explicitly here so that we actually see what's going to happen here. Okay, so d theta 2 star, d theta 2, d theta 1 star, d theta 1. So let's look at theta 2 star. Theta 2. Well, this will integrate to 1, but only when we pulled it through. Only when we pulled it through theta 2 star, so there's a minus sign. So we get one minus sign. Now we have the theta 2 star term. That comes out to be a plus sign automatically. Then we have the theta 1 star, theta 1. Another minus sign because we have to pull it through the theta 1 star. Okay, so two minus signs. So this thing is A11, A22. That's the first integral. The second integral, this one works better. Theta 1, two minus signs, three minus signs, bingo. Theta 2, so we got three minus signs, right? Okay. Theta 2 star with theta 2 star plus 1. Okay. Now theta 2 with theta 2, well this guy is gone, so that's a 1. And then theta 1 star with that, again a 1. So we had three minus signs, so we have minus A12, A21. Well this of course is the determinant of A. Well, I'm not going to try to prove it in general, but in fact it works in general. So for an arbitrary matrix A, the Gaussian integral e to the theta dagger A theta, product of all these d theta star d thetas, gives you the determinant of that n by n matrix. And the Gaussian case, let me just remind you of the bosonic case. The bosonic case would be e to the minus, let us say, alpha star A alpha. And now, what would we be doing? What we'd be doing is d. Let me just try to get this. All right, all right, let me just think a second. All right, let me give it to you for real variables. So F transpose A F product dF. This thing is square root of, and there are n of them, pi to the n over the determinant of A. Integrating minus infinity to plus infinity. The reason why you have to be a little careful here about, and not just say F star F, is, it probably works, but let me just quote the one that I have memorized. All right, so that's a very important Gaussian integral, and notice what's going on here. The fermionic one gives you determinant of A. The bosonic one gives you 1 over determinant of A. In one way of looking at quantum field theory is that this is where the worst divergences come from. So you see, if you have a theory in which bosons and fermions are treated symmetrically, the bosonic determinant is canceled by the fermionic determinant. That's the idea with supersymmetry. The problem, of course, is that then you expect that you have a fermionic partner to every boson particle of the same mass, and obviously in the real world we don't see that. And the upshot is that supersymmetry has to be broken, and so this advantage goes away. And it doesn't totally go away because if you have the same number of modes, the same number of fermionic modes as bosonic modes, then the worst part of the divergences cancel. So it's not totally hollow. So far we haven't seen supersymmetry at the LHC. We may see it at some point, let us say March or April of this year, and or it just may not be there. We've only got a minute left. I think maybe I should just pause and ask for questions.
Yeah, I have a question.
Yeah.
Why do we get a divergence there?
Why do we what?
Have a divergence there.
Oh, all right. Great question. Okay, what is this matrix A? Well, suppose these F's are, so to speak, the classical fields at different points in space-time. Then what is A? Well, A would be d4th x, we're talking about in other words, this quadratic form would be an integral of something like a half phi star, well, you know, all these different terms, d mu phi, like that, plus a half m squared, phi squared, and so forth. Okay? The determinant is the matrix A is the coefficient of the quadratic form in phi's, thought of as, well, here it's kind of like phi. It's diagonal, this term is diagonal, but this term isn't diagonal because it's sort of nearest neighbors. So if we put this thing on a lattice to define the functional integral and then let the lattice spacing go to 0, you see that this matrix A has d4th x. Well, that's the 4th power of the lattice spacing. So it's a to the 4th. And then it's phi I, phi j, a, well, it's not aij anymore. It's whatever the stuff is. But the point is the matrix A has the lattice spacing to the 4th power in it, and so we've got a divergence here. So that's basically what's going on. So, all right, so any other questions? All right, let me. Oh, sorry, bad pitch. All right, any other questions? All right, so let's turn it off and go listen to the president.